Combinatorics, Lecture 6, Problem Session. Problem 1. 6 friends go to a theater and have tickets for seats 12 to 17 in row 5. Part A. In how many different ways can they sit if there are no restrictions? Part B. In how many different ways can they sit if two of them, say A and B, must sit next to each other? Part C. In how many different ways can they sit if two of them, say A and B, should not sit next to each other? Solution. For part A, we know that we have 6 seats and 6 people, and we need to place these 6 people onto these 6 seats with no restrictions. So we are talking about permutations of 6 elements, and so the answer is 6 factorial. That's a number of all possible permutations of 6 elements. For part B, that's when two friends must sit next to each other. Let us construct a seating where these two friends sit next to each other. So first we choose 2 adjacent seats for these 2 friends. Such a pair of seats can be uniquely determined, say, by the seat with a smaller number, and then the possibilities are 12, 13, 14, 15, and 16. So we can do this in 5 different ways. So there are 5 possibilities to pick a pair of adjacent 2 seats among 7 seats in a row. Next, we place our 2 friends on these 2 seats, and this can be done in 2 factorial different ways, because we are talking about permutations of 2 people, and 2 factorial is equal to 2. And finally, we have 4 seats left and 4 friends left and no restrictions. So the remaining people can be placed onto the 4 seats in 4 factorial different ways. Since all these steps are independent of each other, then using the rule of product, we deduce that the total number of seatings available for part B is 5 times 2 times 4 factorial, and that's 240 possible options. So this solves part B. For part C, let Q be the set of all possible seatings without any restrictions. Let X be the set of all seatings in which our 2 friends sit next to each other. And let Y be the set of all seatings in which our 2 friends do not sit next to each other. Then Q is the union of X and Y, and X and Y do not have any common elements, so the intersection between X and Y is empty. And so, by the rule of sum, the cardinality of Q is equal to the cardinality of X plus the cardinality of Y. Consequently, the cardinality of Y equals the difference between the cardinality of Q and the cardinality of X. From part A, we know that the cardinality of Q is equal to 6 factorial, which is 720. And from part B, we know that the cardinality of X is equal to 240. We deduce that the cardinality of Q is equal to 720 minus 240, and this gives us 480. And this completes problem 1. Problem 2. A library has 5 mathematics books, 7 physics books, and 9 biology books. In how many different ways can one place all those books on one shelf, such that books in the same subject are placed next to each other? Solution. Due to the condition that books in the same subject are supposed to be placed next to each other, we can start our placement by choosing in which order the subject will appear on the shelf. We have 3 subjects, mathematics, physics, and biology, and no restrictions, so there are 3 factorial different ways to choose the order of subjects as they will appear on the shelf. Next, within the subject of mathematics, we have 5 books, so there are 5 factorial different ways to place those books on the shelf next to each other. Within the subject of physics, there are 7 books, so there are 7 factorial different ways to place these books on the shelf next to each other. And within the subject of biology, there are 9 books, so there are 9 factorial different ways to place the books in biology on a shelf next to each other. And of course, the number of ways to do something for each step is independent of all the previous steps. So this means that we can apply the rule of product and conclude that the answer to our problem is 3 factorial times 5 factorial times 7 factorial times 9 factorial. Problem 3. An examination hall has 30 desks with 2 seats at each desk. In how many different ways can one place 10 mathematics students, 10 physics students, and 10 biology students in this hall for an examination, such that no students from the same program sit at the same desk, and additionally, no mathematics students sits at the same desk with a physics student? Solution. This is a very non-trivial problem, and the answer will not be very nice. So we will use both the rule of sum and the rule of product many times during the solution. To start with, for I between 0 and 10, let us denote by Qi the set of all possible placements in which exactly I mathematics students sit alone at their respective desks. Note that, of course, all these Qi's are disjoint, and so by the rule of sum, the answer to our problem is the sum over all I between 0 to 10 of the cardinalities of Qi. So let us compute the cardinality of each Qi separately. To construct a placement in which exactly I mathematics students sit alone, we first choose these students. So we have 10 mathematics students, we need to choose I of them. This can be done in 10 choose I different ways. We can place the first of these students in the hall in 60 different ways because we have 60 seats. We can place the second student now in 58 different ways because one desk is now occupied and these students should sit alone. So we only have 58 different ways to place the second student, and so on. We can place the I student in the hall in 60 minus 2I plus 2 different ways because I minus 1 desks are now occupied. Next, we can choose 10 minus I biology students to sit with the remaining 10 minus I mathematics students in 10 choose 10 minus I different ways. Note that this is the same as 10 choose I different ways. So here we use the condition that mathematics students cannot sit with physics students, so it's only biology students which we are choosing here. Now we have 10 minus I mathematics students and 10 minus I biology students, and we need to pair them, 1 mathematics students and 1 biology students. This can be done in 10 minus I factorial different ways, because this corresponds to the permutations of 10 minus I elements. Now for these 10 minus I pairs, we can choose desks at which they will sit in 30 minus I, choose 10 minus I different ways. I desks are now occupied with math students which sit alone, which means that there are 30 minus I desks which are left, and we need to choose 10 minus I of these. Next, we have now 10 minus I pairs and 10 minus I desks. So we assign a desk to each pair in 10 minus I factorial different ways. Now each pair can be placed at its desk in 2 different ways. This is 2 factorial permutations of 2 elements. So our 10 minus I pairs can be placed in 2 to the power 10 minus I possible ways because the placements are independent, so we can use the rule of product. Great. We are now left with 20 desks, 10 physics students and I biology students, and the only condition that we have is that students from the same program should not sit at the same desk. So let us place physics students first. The first student can be placed in 40 different ways. We have 40 seats. The second student in 38 different ways, because the student cannot sit next to the first student, and so on. The last student in physics can be placed in 22 different ways. We now have 10 free desks and 10 seats next to physics students, and we need to place I biology students here. For j between 0 and I, consider the situation when exactly j biology students sit next to physics students. We can choose these j students in I choose j different ways. We have I students, we need to choose j. We can choose j out of 10 seats which are next to physics students in 10 choose j different ways. And we can place j students onto these j seats in j factorial different ways. Great. Now we have I minus j biology students left, and we need to place them. We can choose desks for the remaining biology students in 10 choose I minus j different ways, because we have 10 desks and I minus j students. We can assign one desk per student in I minus j factorial different ways. And we can place each of these students at a desk in two different ways. So 2 to the power I minus j in total, because we have I minus j students, and we use the rule of product. Okay, so now by the rule of product, we have I choose j times 10 choose j times j factorial times 10 choose I minus j times I minus j factorial times 2 to the power I minus j ways to place our physics and remaining biology students such that exactly j biology students sit next to physics students. We can now use the rule of sum, and to get that there are sum over all j between 0 and I, and then the expression which I just read, I choose j, 10 choose j, j factorial, 10 choose I minus j factorial, 2 to the power I minus j. So this is the number of ways to place our physics and remaining biology students. So here we can see that we can simplify. We have j factorial here, and there will be j factorial in the denominator for 10 choose j. Similarly, I minus j factorial and I minus j factorial in the denominator for 10 choose I minus j. So we can simplify this expression to the sum over all j from 0 to I factorial, 10 choose j, 10 choose I minus j, and 2 to the power I minus j. This is about placing physics and remaining biology students. Now we still have our parameter I, that's the number of mathematics students which sit alone. And for this fixed value of I, we use the rule of product and deduce that the number of placements in which exactly I mathematics students sit alone equals 2 to the power 10, 30 factorial divided by 20 factorial, 10 choose I, 10 minus I factorial, 30 minus I choose 10 minus I, 10 minus I factorial, 2 to the power 10 minus I, 2 to the power 10, 20 factorial divided by 10 factorial, and then our sum over all j from 0 to I factorial times 10 choose I, times 10 choose I minus j, times 2 to the power I minus j. So we can simplify this expression to 2 to the power 30 minus I times the fraction where the numerator is 30 factorial times 30 minus I factorial divided by 20 factorial. And then we have our sum over all j from 0 to I, 10 choose j, 10 choose I minus j, 2 to the power I minus j. And now we finally use the rule of sum and add this up over all I to get our final answer. We will have double summation, sum over I from 0 to 10, sum over j from 0 to I, 2 to the power 30 minus j, 30 factorial times 30 minus I factorial divided by 20 factorial, and all this multiplied with 10 choose j times 10 choose I minus j. And this completes our solution. As you see, the answer is highly non-trivial. Problem 4. A full binary tree is a rooted tree in which each node has either 0 or 2 children. For a non-negative integer k, determine the number of full binary trees with k plus 1 leaves. Solution. To start with, let us do a few small cases by hand. Denote the number we are looking for, so the number of full binary trees with k plus 1 leaves, by ak. If k is equal to 0, we just have one root, so it's just the root, so a0 is equal to 1. If k is equal to 1, we need 2 leaves. We only have one tree, namely we have a root and it has 2 children, and these children are the leaves. So a1 is also equal to 1. If k is equal to 2, we have 2 trees. So the first is the root with 2 children. One of these children has no children on its own, and another one has 2. And this can be the left one or the right one. So this means that a2 is equal to 2. And for k equal to 3, we have 5 trees. Namely, these are the trees which we see here on the picture. So a3 is equal to 5. So the first tree is we have a root, and then the right child, which is childless, and then it has a left child that has 2 children, the right is childless, the left has 2 children. Or the mirror flip of this, it's a second tree, and the third tree is where we have left and right children. Left child is childless, the right child has 2 children. Here the right is childless and the left has 2 children. The mirror flip of it. And the final tree is the root has 2 children and each of them have 2 children each. That's it. And now we see that we have a sequence 1, 1, 2, 5. And here we need to start suspecting that the outcome might be given by Catalan numbers, because 1, 1, 2, 5 is the start of the Catalan sequence. So it looks like for our parameter k, the answer ak should be ck minus 1, the Catalan number for the parameter k minus 1. So the question is, which classical problems about Catalan numbers work similarly? And one of the problems which we can remember is that ck minus 1 enumerates possible bracketings of the expression x1 times x2 times and so on times xk for a non-associative binary operation. So the question is, can we construct a bijection between such bracketings and our full binary trees? And here the idea is that let us write our x1, x2, and so on xk as leaves in our tree from left to right. So here is an example how this is done for our trees with 4 leaves. So k is equal to 4. So for the first tree, we write x1, x2, x3, x4 like that, x1, x2, x3, x4 like that. Here x1, x2, x3, x4, x1, x2, x3, x4, and finally here again x1, x2, x3, x4. And now the question is, how can we interpret our tree as a bracketing of the expression? So, for example, we have this tree, the root, with x4 on the right, then the child on the left, which has still child on the left and on the right. The right child is x3, and the child on the left has 2 children, x1 and x2. And it's quite suggestive that here the notion of parenting should correspond to bracketing. So this root has x1 and x2 as children, so we bracket x1 and x2. This root has this root and x3 as children, so we bracket the bracket of this root and x3, and so on. So this tree corresponds to the following bracketing. We bracket x1 and x2, then we bracket the outcome with x3, and then we bracket the outcome with x4. Similarly, if we have this tree when the root has 2 children and both of them have 2 children each, then for the left child of the root, it corresponds to the bracketing of x1 and x2. The right child of the root corresponds to the bracketing of x3 and x4, and then the root itself corresponds to the bracketing of the 2 outcomes. And it is clear that this correspondence is bijective, So this defines as a bijection between full binary trees and bracketings of expressions for non-associative operations. Since we know that the second one is enumerated by Catalan numbers, we get that the answer to our problem is also given by the Catalan sequence. And this completes the proof. Problem 5. Let k be a positive integer. In how many different ways can one connect 2k different fixed points on a circle drawn in a plane by k chords such that the chords do not have any common points, also at the end points? And remark, two connections that can be continuously deformed into each other without any crossings are considered equal. And again, to start with, let us do a few small cases by hand. Denote the number we are looking for by b sub k. If k is equal to 1, we have 2 points and there is only one way to connect them by a chord, so b1 is equal to 1. If k is equal to 2, we have 4 points and there are 2 ways to connect them via non-crossing chords. So we write the points on a circle as vertices of a regular n-gon. In this case, it will be a square. We have points 1, 2, 3, and 4. And the first possibility, we connect 1 and 2 and 3 and 4. And the second possibility, we connect 1 and 4 and 2 and 3. We cannot connect 1 and 3 and 2 and 4 because they will cross. In the case k is equal to 3, we will see that b3 is equal to 5. So we have points 1, 2, 3, 4, 5, and 6. We can connect 1 and 2, 3 and 4, 5 and 6. We can connect 1 and 6, 4 and 5, 2 and 3. We can connect 1 and 2, 3 and 6, 4 and 5. We can connect 1 and 6, 2 and 5, 3 and 4. And finally, we can connect 1 and 4, 2 and 3, 5 and 6. So again, we see the sequence 1 to 5. And this kind of suggests that we might be looking at a new version of Catalan sequence. So, how do we define a bijection between our non-crossing chord diagrams and some other objects that we know is enumerated by Catalan numbers? So we have 2 k points, so we use k chords. So we need an object which is enumerated by Catalan numbers, ck, and which uses k ingredients. So let's do the following trick. For a chord connecting vertices I and j, where I is smaller than j, we call I the starting vertex and j the terminal vertex. Now let us read our chord diagram in the increasing order of vertices, starting from vertex 1, and we record 0 for each starting vertex of the chord and 1 for each terminal vertex of the chord. For example, the diagram where 1 and 2, 3 and 4, and 5 and 6 are connected will read 0, 1, 0, 1, 0, 1. Because 1 is a starting point, we have 0, 2 is a terminal point, we have 1. 3 is a starting point, we have 0, 4 is a terminal point, we have 1. 5 is a starting point, we have 0, 6 is a terminal point, we have 1. Similarly, if we connect 1 and 2, then 3 and 6, and then 4 and 5, we will get sequence 0, 1, 0, 0, 1, 1. 1 is a starting point, we have 0. 2 is a terminal point, we have 1. 3 is a starting point, we have 0. 4 is a starting point, we have 0. 5 is a terminal point, we have 1. 6 is a terminal point, we have 1. And in this way, we obtain a 0, 1 sequence with k zeros and k ones. And the condition that we have a non-crossing collection translates exactly into the condition that the number of zeros in each prefix is greater than or equal to the number of ones in each prefix. And this gives us a bijection between non-crossing chord diagrams and what we called light 0-1 sequences during the lecture. And this indeed implies that bk is equal to the Catalan number c. K for all k. Some problems and questions at the end. Problem question 1. How many positive divisors does the number 40,000 have? Problem question 2. A Senate consists of 50 senators and is supposed to elect the Speaker of the Senate and two disjoint subcommittees with 5 members each and a head of the committee in each case. The Speaker should not be in any of the subcommittees. In how many different ways can this be done? Problem question 3. 8 people, let's call them A, B, C, D, E, F, G, and H, are supposed to be seated at numbered seats around a round table. In how many different ways can this be done such that A sits opposite to B and C sits next to D? Problem question 4. 20 identical balls need to be placed in 4 boxes such that each box contains at least 3 balls. In how many ways can this be done? How about the case when the balls are numbered, so they are really different from each other? Problem question 5. How many Catalan passes on a k times k grid visit the diagonal exactly once apart from the endpoints? Thank you very much and see you next time.